Hello everyone and welcome to David's math class. In this video I will show you a problem I saw on Mind Your Decisions channel and a very simple solution to the problem. That is, if you are familiar with complex numbers. So, given an equilateral triangle ABC, we have to show that if we pick a point P on its incircle, then the quantity AP squared plus BP squared plus CP squared is a constant, no matter where we pick the point P. Alright, I will show you the simplest solution I could come up with for this problem. First of all, note that because this triangle is equilateral, then this point O, which is the center of the incircle, is also the center of the equilateral triangle. What can we derive from this fact? So let's just write it down. So ABC is equilateral, and let's call this circle omega, and we'll say that omega has center O. Now, here's the cool part. We will let O be the center of the complex coordinate system on this diagram. And so, this will be the zero. We'll have apex 0. This we let have apex A, B apex B, and C apex C. So, we'll say the following. Let O with apex 0, A with apex A, B with apex B, and C with apex C. Alright. From the fact that ABC is equilateral, which we'll call 1, and that omega has center O, 2, we'll derive the following. So, first of all, let's note that OA, OB, and OC are equal, because this is also the circumcenter of ABC. So we'll write this as A, B, and C have the same absolute value. Now, what is this absolute value? It is R, big R, because it's the circumradius. The small radius will be the apex of this point, which we'll call small p. Alright, so we'll also let p have apex p, and we'll have that p has absolute value small r, the inner radius of the triangle. And now, here's the cool part. We will write this expression in terms of complex numbers. So we'll write this as E of P, an expression in terms of P, which is equal to AP squared plus BP squared plus CP squared, which is equal to, let's see, AP squared will be an absolute value of P minus A squared, and then absolute value of P minus B squared, and then absolute value of P minus C squared. Let me just show you a fact. I think you know by now that the absolute value of Z squared is equal to Z times Z conjugated. Why is that? Well, if you look in the complex plane, Z would be something like this with argument alpha, the angle that it represents in polar coordinates, and then if you have z conjugated, this will be minus alpha. And if you multiply these two together, what you'll get is these two arguments add up and cancel out to 0. And then these two absolute values, which are actually the same, multiply. And you are left with the absolute value of z squared, which is exactly that. Alright? Now, knowing this, let me rewrite the equation. Alright, I've rewritten the expression, and because sum of conjugates is the conjugated sum, we can rewrite this as p minus a times p conjugated minus a conjugated. And now, because this is a cyclic sum, I will just put the sigma, the sum symbol, and the cyclic symbol right here. Now, let us observe that if we get rid of the parentheses and multiply everything together, we'll get a cyclic sum of p conjugated, and then we'll have p a conjugated times p, and then a times p conjugated, we subtract, and then we have a conjugated. Alright, now let's see something nice about this. I'll just write it full for you. Alright, I've written the sum out for you, and now let's just observe a few things. So these three clump up together, and as we have shown before, absolute value of z squared is equal to z times z conjugated, where z is a complex number. So this will turn out to be 3 absolute value of p squared. But since absolute value of p is r, then this will be 3r squared. Alright, now this we add up together and we'll have negative a plus b plus c conjugated, because sum of conjugates is conjugated sum, and p right here. Now observe that a plus b plus c, wait, something went wrong here. Alright, the sum of these three is actually the 3 times the coordinate. Why? Because this is also the center of weight, but since this is 0, it means that the sum of these three cancel out and you're left with 0. So this will cancel out, and now notice that we get the same thing, but it is conjugated. So this sum right here, you'd have something like a plus b plus c times p conjugated, and this also cancels out because a plus b plus c is 0, a plus b plus c conjugated is 0, and then finally, if we add up these three, it will be, according to this formula, that would be absolute value of a squared plus absolute value of b squared plus absolute value of c squared. And according to this, to the fact that these three are actually equal to the radius, this would be just 3r squared. Oh, right, so we're left with 3 small r squared plus 3 big R squared. Let me just rewrite it for you. Alright, so I've rewritten it for you. And now, here's the thing. If we look at this triangle, I'll zoom out for you a bit. So this would be the contact circle. It's not exact, but you'll see what I'm about to do. So this would be the origin. And this would be the radius, the small radius. And then this would be the big radius. But hey, this is 30 degrees, right? Because This is also the center of the triangle, so it bisects this angle. And in the ABC triangle, we know that because ABC is equilateral, the B angle is 60 degrees. Now, if we just get rid of everything, let me just call this point X for no apparent reason, just, so we have something to call it. We are left with this nice triangle with R here, and this would be big R. And since this is a right triangle, we have that sine of 30 degrees is small r over big R. But sine of 30 degrees is a half. So we have that a half is equal to r over r, small r over big R. And then that means that big R is equal to 2 times small r. And now if we put small r in here, we get that the expression which we're searching for, this sum, is actually equal to 3r squared times plus 3 times 2r all squared. And this is going to be 3 times 2 squared is 12 plus 3, 15r squared. So this is the final result. Let me just write it out for you. Alright, so this is the final result. And because the radius of the incircle does not depend on the choice of the point P on the incircle, this sum will be constant no matter where we choose the point. And that is the proof. So this is constant. Thank you for watching, and see you in the next episode of David's Math Class. Goodbye.